Well, it's a pleasure to welcome you here for this Wednesday seminar. So this afternoon we're going to have two talks, the first of which is given by Vojkan Jaksic from McGill University, and he'll tell us about conductance and the AC spectrum.
So many thanks for the invitation. It's a great pleasure to be here again. The last time I was here was in 94, 95, so lots of things happened in the last 20 years. So this talk concerns the link between two different directions of research. So one is the transport theory of non-equilibrium quantum statistical mechanics, and in partly mathematical developments in this area over the last 15 years, and spectral theory of Jacobi matrices. So the connection between these two directions goes back to the 1970s and foundational work of physicists of Thouless, Anderson, Lee, Landauer, just to mention a few, who developed the transport conductance theory of 1D samples. Mostly they were focused on random samples, but not necessarily. And looking of the importance this theory played in physics, one would think that this theory, since it preceded modern developments in spectral theory, that it would actually motivate modern developments, but that was not the case to my knowledge. So there is only one piece of work that I know of that really established a connection between these two directions, and this is a PhD thesis of Yoram Last from 1994. It is titled the same, well, it's a very similar title to my talk, Conductance and Spectral Properties. So in his thesis, Yoram has proven some truly fundamental results about quasi-periodic operators, but they were motivated by physics. And the physics part was never published. So I will say it's a very foundational, very deep, and he was 20 years ahead of all of us. So I will, as we go on, I'm still trying to convince him to put it on the web. And as we go on, I will explain where his insight came in. So here are the papers I will talk about. Well, not really talk about, I mean, there are 5 papers in the last few years. And in this talk, I will talk about first and the last. The second and the third will be subject of the talk next week, if that is still scheduled. And the fourth paper I will just mention a little bit as we go on, but I will not discuss in detail if you're sort of interested in a detailed relation between Landauer, Buttiger, and Thouless conductance, which also has to deal with Jacobi matrices. I would be happy to explain that to you. So let me start with a picture of what we are trying to do. So this is sort of a real-life analog of what we will try to do. Suppose you have 2 tanks of water, one which is high and one which is low, and then you have tube connecting them. So there is some potential difference, you can see, because the heights are different, and there will be water flowing from the higher to the lower reservoir. Now, if you imagine that these reservoirs are infinite, or you look at the time scales, which are much smaller than the size of the reservoirs, then this flow will be constant. So the question which you can ask is, you can look, now here I took this picture from web, so this is kind of straight, but the question which you are in principle interested is, by looking at the current, you would like to say something about the tube. Can you say something about, for example, if the tube goes up and then comes down, there will be no current, because it's, so we would like to detect the shape of the, or something about some fundamental aspect of the tube from the current. So we will do this in a context of electronic transport. So instead of water reservoirs, we will have a battery, or we will have 2 electronic reservoirs, which are at different chemical potentials. So chemical potential is the difference of the chemical potentials is the voltage, and this is same as this elevation here. So the tube here will be replaced by sample, sort of piece of wire, and because of the chemical potential difference, there will be current flowing from the left to the right reservoir. And so the questions which we would like to ask is, what can we understand about the sample by looking at the current? And the question which we will be interested in is different between insulator and a conductor. And so how we will define insulator or a conductor? So we will look at a transport or a conductance. So the conductance is just transport divided by the voltage differential. So it's the same thing. And so if this transport survives as you take L to infinity, then it will be a conductor or metallic regime. And if it does not survive as L goes to infinity, it will be an insulator. And this is the idea which I think physicists had in the 70s, how they approached the problem. Now, to do anything here, first you need a mathematical model in which you're going to describe on a quantum mechanical level what do you mean by this picture. So after you have a mathematical model, you need a formula for the current, which should be proven from the first principles of quantum mechanics. And once you have the formula for the current for a finite sample, you have to study this formula in the large L limit and connect it, if you can, to the notions of conductors or insulators. That's okay? So let us start with the mathematical model, and I will just make it as simple as possible. So our sample will be just the Hilbert space of the sample is finite dimensional. It is just L2 of a finite interval 1 to the L in Z. And Hamiltonian of a sample, actually you have to be careful, but it's a Hamiltonian, HL, will be just a discrete Schrödinger operator. This is a Laplacian, this is a potential, restricted to this interval 1 to L. You can put whatever boundary conditions you want, let's say Dirichlet, because it will not matter for what we will try to do. Now I had to describe reservoirs, and I have to start with what we will call one electron data. So it's easy, one can be quite general. So one electron data, so this will be the Hilbert space of left-right reservoir. This will be energy operator of left-right reservoir, which is bound itself a joint operator on big H. And this will be a unit vector in our Hilbert space, which will allow us to couple the sample to the reservoir in a simplest possible way. So I can assume, you can trust me, that it does not change anything if I assume that psi is a cyclic vector for H. So if I do that, then I can pass to spectral representation. I can assume that my Hilbert space is just L2 of R. This is a spectral measure for HLR or psi LR. HLR is the operator of a multiplication by the variable E, and this is just going to be a constant function 1. So now we need to connect electron reservoirs to our sample, and we are going to do this first on one electron level. So to do so, we just take a direct sum of the Hilbert spaces. So this will be left part, this will be right part, this will be central part. Electron can be here or here or here. The non-interacting Hamiltonian is just direct sum of this left energy operator, then sample, then right energy operator. And then one full, what I will call one-body Hamiltonian, would be just H0 plus V of t, where V of t is a tunneling junction, how people call it. So this is just rank 4 operator. So this is, if you look at the picture, if electron is here, it can jump to the left reservoir to the weight function psi L, and if it is here at L, it can jump to the right reservoir to the weight function psi R. This is just a Jacobi matrix, if you can recognize, because I can just represent this by L2 of n. This could be just it's any cyclic Hilbert space. Any cyclic problem could be mapped to a Jacobi matrix. So I will not do so, but one can do so if one wants to have a spatial structure. So I know that people here might not be familiar with the quantum field theory, and I will go very, very quickly just to give you a taste of how one sets up the problem in the right way. There is a reason that one really would like to do things from the first principles. And right now, from the first principles, we don't have one electron, we have an electron gas. Right? I mean, you need, you want to have a current flow. If you look at your wire, I mean, you don't have one electron flowing, but you have large of them flowing in the same direction. So to set it up mathematically, one has to use a little bit of quantum field theory. So here are the words one starts with a Fock space over H. So this was one body Hilbert space which I had here, this direct sum. So you form a Fock space over that, and you take anti-symmetric one because you're dealing with electrons. So Fock space starts with a, let's say, H plus direct sum, H cross H, tensor product, which means you describe two particles, then direct sum H cross H cross H, which means you take three particles and you go up to infinity. Hamiltonian is a second quantization of one body operator that we have here. And we need to say what we can measure. It is not true that right now you can measure everything. So we have algebra of observables, which is just a family of bounded operators on our Fock space, which are generated by annihilation and creation operators in the Fock space. And we have a state. So we have to describe the state of the system, if you look at the picture, where we have electrons on the left being higher than electrons on the right. And to do so, you cannot do that with the density matrices, so you cannot do that with the vectors, because the total energy of that state is infinite. So you have a positive linear functional on the state of, on the algebra of observables. It's just analog of a measure, of a Gaussian measure in a fermionic setting. And it is constructed from the first principles of statistical mechanics. I will not write you down the formulas. So this is all well defined, and we have now charge current observable. This is the observable which measures the charge flowing from the left reservoir to the right reservoir. And that is just a commutant between the full Hamiltonian and the number operator of the right reservoir. So number operator measures how many electrons do we have. Of course, in this state, we have infinitely many electrons. So, and this will not be a well-defined observable. But commutator is well-defined. It is in the algebra of observables. And it involves in time in the Heisenberg picture. And so here is our steady state current. So you take this observable, you evolve it in time, you take its average value in our initial state, and you average over time and take t to infinity, and hope that limit exists. And this is the number which is of fundamental physical interest, which describes the steady state electronic energy charge current from the left reservoir to the right reservoir in the large time limit. If you sort of want to write this more formally, you can say, if you just differentiate and integrate this relation, you end up with this. Except that this number here is infinite and this number here is infinite, but their difference is finite. Because the system is infinite, the total, there is infinite number of electrons. But if I look how much the number of electrons is changing, that is a finite number. So if you put reservoirs in a box, then everything is finite, and this formula is the same with this one. This one makes sense in thermodynamic limit, and this one does not. Okay, so it is not hard, and I mean, anti-symmetric Fock space is in chapter 2 of Reed and Simon, volume 1. But
this is a free electron.
This is a free electron. I will talk about interaction in the end of the talk. So it is a free electron gas without any interaction at the moment. And for most of the talk, it will be like that. So the question is then, what is this limit, right? And this limit, the formula, so to speak, goes to 70s, to the work of Landauer, and Landauer and Buttigieg later on. And it's a very simple formula. It's just integral from between the lower chemical potential to the upper chemical potential, and there is a function here. And this function is completely expressed in terms of one electron data. So this was a coupling constant lambda, which I had put here just for a convenience. It's nice to have it. And then we have a matrix element of the resolvent with a vanishing imaginary part. So it's a boundary value of the resolvent between initial point and end point of the sample. And this is the density of the absolutely continuous part of the spectral measure for our coupling between left and right. So this is kind of density of the states of the left reservoir, and this is density of the states of the right reservoir. So if you multiply this with 2 pi, so this is a number which is between 0 and 1 over 2 pi. If you multiply with 2 pi, this is precisely the transition probability per unit time that electron can move from left reservoir to the right reservoir. And how it is computed, it is just a stationary scattering theory. It is a stationary scattering theory between pair H and H0. You re-express object which you have here in terms of one-body theory. You use that this is quasi-free state, you write things right, you take the limits, and you compute.
But in scattering theory, you usually don't have square. And what does it mean?
No, wait a second. This is a scattering, you compute a scattering matrix. This is off-diagonal element of the scattering matrix for the pair H and H0.
But how do you understand this integral? It is not clear.
What do you mean, how do you understand this integral? This
Singular,
is a measurable fund. What do you mean? This is on the real axis.
Yes.
So
This is very singular.
why it is very single? It's a number between 0 and 2 pi. It's a bounded function, bounded measurable function. It's not obvious, but this is 2 pi times this is off-diagonal element of the scattering matrix. That is a number between 0 and 1. You have to because this is very singular. But this H contains, you're absolutely right, this is a very singular object by itself, but it contains these 2 parts which modulate it. And so this is number between zero. This is a formula exact. If you want to look at the chapter 8 of your book, it is it is from there. And but you can of course do it by hand because this is a rank 2 perturbation theory. So you don't need to read a chapter 8 of year 5 stationary scattering theory. If you want to do a more general situation, then you have to. So I mean, the interesting fact is that although this was postulated in 1970 and it was not proven until 2007, and it's very hard to explain why it was not proven until 2007, but it's just the way it was, and I think partly it was because people just did not set up the problem right by using elementary quantum field theory. There is another, so this is a fundamental formula in physics. There is another one which is equally famous and is Tauer's formula, which when you read a Tauer's paper, I mean, it is defined sort of in a very, very physical term, but there is a way to understand it as a very special case of the Landauer-Butticher formula. So what are we going to do is remember that we have those reservoirs, left and right reservoir. So we are going to make the reservoirs to come from a perfect crystal. So here I have a sample which has minus d plus v, and I'm just going to repeat that sample to the left and to the right. And then I'm going to keep my sample here. I have a perfectly periodic operator. I'm going to declare this part one reservoir and this part another reservoir. So it's a perfect crystal. I have unit here, that's sample, and the rest are the reservoirs. So in this case, the scattering is reflectionless. My full operator is just periodic operator with a period of the sample. And this number here is either 1 over 2 pi or it is 0. It is 1 over 2 pi if you are on the spectrum of the periodic operator, and it is 0 otherwise. So if you look at this formula, then this becomes just a characteristic function of the spectrum of the periodic operator. And here you have then 1 over 2 pi, Lebesgue measure of intersection of the spectrum of the periodic operator, has finitely many bands, with interval determined by the chemical potential. And this is a Tauer's formula. This is something that many people in this audience have already seen, purely in terms of the spectral theory, but it is a fundamental physical object. And usual wisdom is that Landauer-Butticher current is less or equal than Tauer's current and is maximized in a certain sense if you have most optimal reservoirs. And this is true, but you have to be careful how do you interpret this. And the paper, which I will not talk about, is involved with proof, first formulation and then proof of this relation. One has to introduce an intermediate notion of the conductance that is called a crystalline Landauer-Butticher formula, and then you can state and formulate a theorem regarding this inequality. Okay, so what is our goal? So our goal is right now we're going to look at extended samples. So what is extended sample? That means that we will have one-dimensional Schrödinger operator, discrete one, on a half line. If I restrict this operator to the interval 1 over L, I have my finite sample. Now, because this is an infinite, this is on a half line, it may have an absolutely continuous spectrum, and also the essential support of the absolutely continuous spectrum, which are non-trivial. So these two objects sort of intuitively correspond to what we should think about the transport part of our Schrödinger operator. Now, so our goal is to identify mathematical characterization of the conducting regime. That means absolutely continuous spectrum of this operator, or essential support of the absolutely continuous spectrum, with a physical characterization of the conducting regime, the way it was defined by physicists in the 70s. So these sets, in hopefully some precise mathematical sense, will be precisely the set of energies at which the charge transport of the finite samples will persist in the limit L is going to infinity. Okay? So we started with the first principle, we derived these conductance formulas from the quantum mechanics, and now when we have a dynamics for these formulas, we would like to use them to characterize absolutely continuous spectrum. Maybe it's not true, we don't know. And so that was the beginning of our program in 2012, I don't know. But the first thing to do is to maybe simplify our life and look at the linear response theory. So in linear response theory, that means we fix right chemical potential at some number E. We take left chemical potential to be E plus epsilon. And then we just look at our formula here. So we have J from E to E plus epsilon. Now this is E prime, dE prime. And then for Lebesgue almost all E, you will have this relation. That the current on the first order of perturbation theory is just a density plus vanishing term. And so one can introduce then the set of energies at which the Ohm's law will persist. The infinitesimal current will persist. And we say that the set of energies is the lim inf of dFL of E is equal to 0. And then we made a conjecture in 2013 that this set here will be precisely the essential support of absolutely continuous spectrum. It's kind of very nice. The essential support of the absolutely continuous spectrum hopefully would be precisely the set of energies where the transport persists in a large sample limit. And so after you make a conjecture, you try to prove something. And to state the result which we have to introduce a transfer matrix of the operator H of S. So everybody in this audience knows what a transfer matrix is, how do you build a solution to the half-line Schrödinger equation. It is just a product of individual transfer matrices that we have here. So E is the energy.
What about V?
V is here.
Kind of V.
Any V. My V is totally arbitrary.
He hasn't made a statement.
Yeah, but but the result here is true right now without any conditions. This theory should hold for any potential V. It's like range theory, and it's kind of you have a general structural result. Right, so V is just a function from Z plus to the real line, and this is the result which we got. I mean, there are several results, but this is the result that the set here, which the current will persist, is precisely the set of energies where transfer matrix is bounded. So this is equality modulo of set of Lebesgue measure 0. So these are always the same. And now if you have this and right now I have to remember the name, the Lana is sleeping, so I should not remind me the name. So it's anyway. It was reproven by Barry Simon, but it's all the result in that the set of energies where transfer matrix is bounded is always contained in the essential support of the absolutely continuous spectrum. For any. And so once we realize that, then because there is a connection with transfer matrices, that if this is really true, what we hoped, then people in spectral theory must have looked at that before us. Because right now it's really statement about transfer matrices, not statement about the transport. And a quick Google search turned that this is actually, at that time, was celebrated conjecture posed by others that is called the Schrödinger conjecture. And I think the name Schrödinger conjecture is very attractive. It was called by academician Maslow, I believe, and who also had the first counterexample, which turned out to be wrong. So it was okay. Right now, you call Yoram Last, you talk to Barry Simon, you learn that this is actually they consider one of the most fundamental open problems in the spectral theory of one-dimensional Schrödinger operators, and it was believed to be true for any potential B. This set's different.
It was not conjectured by Schrödinger.
Well, I mean, he's dead, so we cannot ask him, right? I doubt it was. I mean, basically, I think people use this name. It sounds good in the end of the day. I mean, maybe Lana has a different historical perspective.
Schrödinger had some vague sentences suggesting that he thought that basically everywhere on the continuous spectrum, of course, he wouldn't distinguish between singular continuous and right.
Okay, so Lana knows history better, so apparently Schrödinger wrote something.
But sort of on the level of your quantum mechanics 1 class. All the physicists
would believe that generalized eigenfunctions
like
are bound.
wave-type solutions and
Exactly.
states.
What happened was that it is not true, and Arthur Avila was kind enough to send us preprint of his paper before it was submitted for the publication. So Arthur Avila had a counterexample. So it's published now. And the amazing part of this counterexample is that not that he constructed some strange V, or he used the logic to show that V exists, but he actually has done this in a setting of the ergodic theory. So there was, I mean, okay, everybody he knows what does it mean to have an ergodic Schrödinger operator. So he can construct a particular uniquely ergodic example where one has ergodic potential for which with the probability 1, the difference between the essential support and the set tau, where transfer matrices are bounded, has a strictly positive Lebesgue measure. So this is astonishing, right?
There is no concrete example.
Well, if the probability 1 is not concrete enough for you?
So, no, that is a completely different question.
So it's good that the Pasteur is not here and he would have a heart attack.
No, two completely different problems.
Yeah, but
With existence, if you wish. But with probability 1.
The existence, yes.
if you
The
okay.
existence.
Okay, all right. Anyway, so at least, I mean, to me it was an astonishing result because I certainly did not expect this because of the Kohtani theory. In the ergodic setting, actually, if you replace lim inf with lim sup in this definition, then we actually knew that conjecture is true. We never published that, but that is true. And also there is a result about Dave and Simon, very classical result that essential support of the absolutely continuous spectrum is precisely the set of energies where lim sup of the averages of the transfer matrices is less than infinity. It's not, these are the statements with probability 1.
And what is D?
Where is D? D is my function, which it is here, right? This is my density of the transport okay.
And what kind of distribution you have on the
None.
set of potential?
None. For Avila's counterexample, so he starts with it's a very, very elaborate construction. So it's an ergodic process. So he has a function V from, I think, circle, and then he constructs he perturbs very, very carefully periodic problems to arrive at the limiting object, which has the right. So it's and also if you look at the fact that this becomes unbounded, it is at the way you fix, there is a set of E's of positive Lebesgue measure, but else for which is this true is extremely sparse. This kind of takes they're essentially exponentially separated from each other. So it's a very rare realizations of L for which one has to blow up. Actually, the advantage to have a junior collaborator is that you make a junior collaborator read a Willis paper and then tell you what is in. So I have to ask Laurent for the details of a construction. Anyway, so right now it does not look good, right? Because so this counterexample to Schrödinger conjecture actually turned out to look like a counterexample to what Towles and Anderson and other people were telling us, that metallic regime is the set of energies where transport should persist, and so right now maybe something is going on with singular icon. We just didn't know what to do. And so the idea was to maybe prove a little bit weaker statement, not to look at the density itself, but just to use original integral. So right now look at a really complete transport, not just Ohm's law. And then it turned out that things are actually okay. So here is a theorem. This is a relatively recent result. It was actually proven last December. So remember that our currents, both Towles and Landauer-Buttigieg, depend on the length of the sample and on the chemical potential. Here, this is familiar object. Just to remind you, this was just the length of the spectrum of the periodic approximation, intersecting interval. And for Landauer-Buttigieg formula, we have this integral here. This is the transmission probability per unit time at the energy E. And then everything works out right. Then the following statements are equivalent. There is the extended sample has no absolutely continuous spectrum on the interval nu R, nu L. We have vanishing of the Landauer-Buttigieg conductance, and we have a vanishing of Towles conductance. In addition, if there exists some absolutely continuous spectrum, then not only that lim sup is bigger than 0, but actually lims infs are bigger than 0. So the currents are bounded for below. This is true for any potential. There is no randomness, the deterministic result. So in this case, right now, you're happy because right now it's always true. And whenever something is always true, the proof has to be structural. Okay, so what is, now this is an expert audience, so you might correct me. So there is a key lemma for the first part of the proof, which says the following. If I take an interval on the energy axis, which has an empty intersection, that interval has an empty intersection with absolutely continuous spectrum, if and only if this integral is vanishing. This is a transfer matrix to the power -2. So I have not seen this result before. It might be known, actually. I don't know. And this is a key ingredient of our proofs, because we actually prove that every of those statements, B and C, is not equivalent to this one, but it's actually equivalent to this one. You will see this power is very natural here. And I tried to prove this for some time without success until I visited Yoram at Hebrew. And there is a key ingredient to prove of this fact which I didn't know. And I was very happy to realize here that anybody I have asked also does not know. And this is a result which is due to Carmona, but is written in a language of a continuous operators and also in a form that's very hard to understand. And then it's in a paper by Krutikov and Remling in a discrete setting, and also in a paper by Berry in a discrete setting with a very, very elegant proof, but very mysterious proof. And it says the following. So let mu d be the spectral measure for our half-line Schrödinger operator and delta function at 1. Delta 1 is a cyclic vector. And you put a Dirichlet boundary condition. And then you take a vector 1, 0. And then if you apply transfer matrix to this vector, you take power -2 and you divide with 1 over p. This is a measure which converges weakly to the spectral measure mu d. If you integrate this with respect to the continuous compactly supported function, then the integrals converge as L goes to infinity. And if you want to have a different boundary condition, not a Dirichlet, you just change this vector. And then for any boundary condition, you can find the right vector. The proof is very mysterious. I mean, it's very beautiful, especially the way Barry wrote it, but you ask him why this is really true, he didn't really provide a satisfactory answer. And once you have this, getting this result is not that hard. So then the proof of equivalence A to B follows from the lemma, from an old result of Last and Simon, that if you fix a sequence, then the essential support of the absolutely continuous spectrum is precisely contained in a set of energies where transfer matrices, lim inf of transfer matrices is less than infinity, so it's contained there. And the result which we have in 2013, that the set of energies where transfer matrix is blowing up is precisely the set of energies where transport is going to zero. So that that dealt with a case B equivalent to A. Now C equivalent to A had a very, very interesting history. And it was proven actually in Yoram last thesis, in ergodic setting. And Yoram used Kotani theory, so there was really no way that his proof can be extended to the deterministic setting that we are working in here. But he has proven something very interesting for you, which I guess everybody in this audience probably knows. So you take your ergodic one-dimensional problem, you cut it at L, and then you repeat it periodically. Then you have a periodic operator. You have some absolutely continuous spectrum, and then you look of intersection of that absolutely continuous spectrum with our interval. And then you take lim sup L going to infinity, and you have a lower bound that is bounded from above by the absolutely continuous spectrum of the full operator intersecting this interval. And this holds with the probability 1. So Yoram, in proof of this statement, Yoram was motivated by the Taurus conductance. This is a Taurus conductance. And he was trying to understand the relation between the Taurus conductance and absolutely continuous spectrum. He was in physics department. It turned out that this relation has a really, at that time, spectacular consequences for the spectral theory of quasi-periodic operators. Because if you have an almost Matthew operator, then the measure of the Lebesgue measure of this intersection, there was a lot of information from the paper of Simon, Avron, and Mush from 1989. And so what Yoram was able to prove from combining this inequality with their result is that for almost Matthew operator, if coupling lambda is less than 1, then for Lebesgue almost all alpha, now everybody knows what almost Matthew is here, and for phases, for Lebesgue almost all thetas, the Lebesgue measure of absolutely continuous spectrum is precisely what it should be, 4 minus 2 lambda. And if lambda is small enough, then actually for all alpha, irrational alpha, and for all, I forgot whether it was, I think it was also for all theta, the spectrum was of the right length. Now it's known that this is true for all alphas and all thetas, but at that time, that was the very famous result. All right, so we need something like this in order to do things in a deterministic setting. And there is a deterministic extension of last result, which is due to Kestesi and Simon in their paper on the Xi function. But this extension works only for the full line operators. It works also in higher dimensions, but it's very important that operator is in the full space. Is a way that the periodic approximations on the half space or on the full space are very, very different. And they use some very specific properties of the periodic operators in the full space. So then, of course, we talked to Barry, and he says the extension should be trivial. And then a week later, he says it's a less trivial. And 2 weeks later, he says he doesn't know how to do it. And all right, so what we can prove for the half-line case is a weaker version of this. We can prove that that this limb soup for any potential V without any randomness is less or equal that this intersection of Lebesgue measure of spectrum of periodic approximation intersecting our interval of chemical potential is less or equal than constant, the limiting object, and then power 1/5, but the constant is 18.7. And if you want to work really hard, you get 16.4, but this remains an open problem. I don't know whether this is true for a half-line operators. And when you think about that, there is a good physical reason why that should be difficult, because the left limits of half-line operators can expand absolutely continuous spectrum, and you really have to fight that. Okay, so the inclusion A implies to C is sort of based on on a very concrete analysis of the spectra of the periodic approximates, and I will not talk about that. So for our purposes, this kind of settles the issue, what is absolutely continuous spectrum, because this also applies to Jacobi matrices. You don't need minus delta plus V. But if it works for Jacobi matrices, then it works for any cyclic spectral problem. So whenever you give me a Hilbert space H, Hamiltonian on that, and a cyclic vector, I can always make a transport problem and characterize absolutely continuous spectrum by the persistence of transport. And everything comes from the dynamics, because Landauer-Buttigieg formula is proven from the dynamics. So one has a neat picture in spite of the Avila's counterexample. So right now one would like to go further, and one would like maybe to say a little bit more, and then I will, since in this audience many people are interested in this topic, I will talk a little bit about many-body theory, and in particular I will turn to many-body localization, but I don't have to do it at the moment. So remember that our starting point was that of an electron gas. It was attached at the ends to two batteries, and these batteries generated a current. We computed the current, and then we related the current to the transfer matrices, and we went on the spectral field. But in that picture, I can allow my electrons to interact. The connection with one body theory will completely break down, but the physical picture is perfectly well defined. So we again have our Fock space, where we have describing an infinite gas of infinite gas of electrons. We have our algebra of observables, generated by creation and annihilation operators. We have our initial state, which describes that at the left and on the right, we put electronic reservoirs at different chemical potentials. And now on my sample, I will allow electrons to interact with a two-body interaction. So this, I can put a constant here, or I can put some function, does not really matter. So whenever the distance between x and y is 1, we have a two-body interaction. This is creating an electron with the delta x. I wrote for delta xx, and this is annihilating the electron with delta x. If you sort of write it in the sectors, it is just a two-body interaction where two particles are next to each other. So it's just the right way to write it if you want to take thermodynamic way. Now we have interacting Hamiltonian. We have our free part, which is just minus delta plus small potential V, and then two-body interaction. We again have a current observable, which describes the flow of electrons even if I add interaction. It is well defined. It's a bounded operator. They're both unbounded, but commutator is bounded. It evolves in time. And now I can define what do I mean by the localization regime of an interacting electron gas. We can say that first we will look at the steady state current when my sample is finite. And then I'm going to remove the size of the sample to infinity. Now, because limits are hard to prove that they exist, we put lim sup and lim sup. And so this will be a localization regime. If this is always going to be finite. This is never going to be 0. But if it vanishes when I take L to infinity, we will say that we have the localization regime. And we have a conducting regime if the opposite limits, lim infs, are strictly bigger than 0. So if the current persists, then we are in conducting regime, we are delocalized, and if the currents are vanishing, we are localized. So this is just a definition, so it is perfectly reasonable physically, and when there is no interaction, when V is equal to 0, this is equivalent by our result that whether we have absolutely continuous spectrum or do not have absolutely continuous spectrum on this interval. So spectral theory is not adequate, I think. It's really a problem in quantum statistical mechanics to describe many body transport. But this definition comes motivated from the one-body theory because there it is equivalent to the spectral characteristic. And now if you would like to go back to what one means by one-body localization, there's a concrete problem. We assume that these are IID random variables, say with densities. And then the question is it true that for all chemical potentials, this object here is vanishing? If this object is vanishing, we would say we have localization, and if it is non-vanishing, then we say it's strictly positive. That we have in. And now, I mean, this is sort of very tempting setup because one can go really far with the conjectures and definitions. One can develop a linear response theory, one can have many body Lyapunov exponents, one can have many statement what should be many body Kohtani theory. One can extend this theory to any dimension because if I have a sample I can just attach two wires at 0 and wire at L and look at the current between 0 and L. And so this is all well and nice, except it is impossible to prove anything. Right? So this we worked really long and hard. And if you look, the amount of effort it takes to prove something that physically looks completely trivial is essentially unreasonable. It takes 150 pages of estimate to prove something that is totally obvious. So we never published anything. But here is a very, very simple problem. If this direction is ever to succeed, forget about having a two-body interaction like here. Assume that electrons interact only when they're on sites 1 and 2. So right now, I have no problem. I mean, right now, this is not an extended interaction. This is just a very, very localized interaction. It's a two-body interaction, but kind of in an absolutely minimal possible one. And so in this trivial case, you would say that involving this minimal interaction does not destroy localization. That cannot be. I mean, that cannot destroy localization. Exponential localization cannot be destroyed by something so tiny. And this is completely optimal. There are really very weak partial results. So this cannot be answered. That would be the first step for young people in the audience. I think it is a very tempting problem, but I cannot say much about it. But Milivoy is young. I was not referring to you, but okay.
Well, thanks very much. Are there any questions or comments?
So what is many body Lyapunov exponent?
So that would be you do a linear, so that's a very good question. So what is one body Lyapunov exponent? Well, this is the way 1 over L logarithm of the transfer matrix goes to 0. So if I look at this formula here, well, I have to come back. This formula here.
Mm-hmm.
So
Philip's formula.
yeah, that's exactly a Fab's formula. Exactly.
No. No.
It's yours. I cannot do that. What?
It is written.
No, but the scattering, this is off diagonal element of the scattering matrix. So this is essential, this is proportional to the norm of the transfer matrix between L and e to the power minus 2. So if I take 1 over L logarithm dL of e, this is going to precisely minus 2 gamma of e. So how we are going to do many body Lyapunov exponent? I have now, everything is translation invariant. It's good to have in translation invariant setting. We are going to take this, we are going to do linear response theory, so we extract the coefficient. And then I take 1 over L log of that, and if that limit exists, we are going to call it Lyapunov exponent, and then we are going to say that in IID setting, the set of energies where transport persists will be precisely the set of energies where the Lyapunov exponent vanishes. So that is true when you don't have an interaction. So that's a conjecture, maybe completely wrong. But This allows you to extend the definition from one body theory to the other body theory, because you think about transfer matrices as what it gives you the linear response theory in the transport phenomena between two electronic reservoirs. Of course, so that would say that this transport here is that this limit is not only going to zero, but it's going to zero exponentially fast. And the rate at which it goes to zero will be the Punov exponent. And that's what happens in IID or in localization regime in one-dimensional set. But I mean, I don't know whether even numerics is done about that. All right.
Other questions or comments? Well, if not, I thank welcome again. And as we stop